Hi guys, so today I'll show you guys how to create an efficient frontier for a risky portfolio of multiple assets and how to find the optimal portfolio based on the efficient frontier. Let's go. Okay, in the historical data part, the first thing we need to do is to update the assets price that you are interested in or which are located in your portfolio right now. In this case, I took the data of the 6 assets in my portfolio. And as you guys can see, I've already uploaded the close price data in this worksheet. And if you guys want to get this data, you can go to investing.com or any other website, but I prefer using investing.com. And for the data, well, I took it yesterday. So the ending date is 5th May 2025, and the starting date is 23 August 2018. I suggest you guys to take as much data as possible because the more data you have, the more accurate the results. Okay, so before we jump straight into creating the efficient frontier, we are going to calculate the daily returns. Okay, to calculate the daily returns, I'm going to take the 1 day price minus the previous day and then divide by the previous day. So that should give me the oh what wait here that should give me the results. So this is the daily return of the 5th May 2025, right? So to make this faster, I want to fill all of the box. So I'm going to paste this formula to the others by copying this formula and then paste to all of the cells in this box. Okay, so you Control C, you go to the bottom and then you highlight the bottom. Okay, and then you go to the top to paste it. Remember to paste the formulas. Okay, so this is the result, and you guys can see the bottom row, it's having some problem, but we don't need it because it's divided with 0. See, you get it. Okay, so after we have collected all the daily returns, we are going to analyze it. So we move on to the next worksheet. Okay, I've already pasted some function, some box, some table in this to make it faster. So the first thing we have to do is to take the average of the daily returns and then multiply it by 252, which is the trading days. Here we take the average function and then we grab all of the data in the FP2 column, Control Shift down, then you multiply it with 252. So after we have calculated the annual return, we're going to wrap it up with the exp function because we are assuming it's continuously compound, and we subtract it by 1. Exp function and then subtract it by 1. So this is the annual return of FPT. And then I want you to paste the formula to the other. And these are the annual return of these assets. Now, what we need to do is that we're going to calculate the standard deviation, which is the risk component of the portfolio. And I will show you how to do it with a single function. It will equal to the var s. The reason why I'm choosing var s over var p is because the data that we take is just a subset sample of a larger population. For example, well, the data that I took, it's only 5 years, but the data of this company have been listed for 10 years. So this is the small size, okay? So we use the var s function, and then we grab the daily return of FET, Control Shift down, and then You multiply it with 252 to analyze it. But the thing here is that this this is just the variance. Now we need to square it down. Take the square root of this. Now we need to take the square root of this by using the square root function. And now you drag to the right side, and now we have the standard deviation of these assets. Okay, so now what we need to do is that we need to assign some weights for this portfolio here, and I want to do it randomly. So what we are going to do is to create 20,000 science scenarios based on the weights and grab them all into the efficient frontier. So to come up with a random weight, I'm going to use the rand function. Rand function. Rand function. Okay. And then you drag it to the right. As you can see that these function give me a bunch of the numbers, the random numbers, but these do not sum up to 1. So I'm going to sum it up by use the sum function. So to assign our weight, I'm going to use this formula. I'm going to take this, divide by the total number, then log it up, and then you drag it to the right, and we have just made a random weight for our portfolio right now. And as you can see that these sum up to 1. Let's sum it up right now. So whenever you press F9, the weights change, but it still sum up to 1, right? And this is what we need because we want the weights to be randomized. Move on to the portfolio summary part. Now the weight has been randomly generated. So let's go ahead and calculate the expected return on my portfolio, okay? We can just use the function called the sum product to calculate the expected return of the portfolio, sum product. Now we grab this array, the annual return, and the weight. So in this scenario, with the specific weight, the expected return is 17%. So now let's come up with the annual standard deviation. The annual standard deviation calculation is going to be based on the covariance and variance matrix. So the reason why we need to use the variance and covariance matrix is because we need to find the correlation between these dogs and also the covariance. And so to create a covariance matrix, you need to go over data, work at the analyze part. But if you don't see it, don't worry. I will show you how to get it. Right click in the ribbon, customize the ribbon, go to add-ins, and then make sure that you manage have the Excel add-ins in here. Press go, check in the analysis toolbar and then solve add-in. Press OK. So we're going to find calculate the covariance. So data analysis covariance. OK. For the input range, we're going to put the daily return that we have calculated in it. We Control Shift down all of the data. Click the label in first row. For the up range, click here. Press OK. OK. So I'm going to fill the blanks by district. Okay. Copy the data. Copy it. A special. Transpose. Transpose. Okay. Press OK. So this will fit with the blanks. Now you copy this and paste it back right here. Paste special. Skip blanks. Okay. So this the covariance and variance matrix. Now we need to calculate the standard deviation. For the standard deviation, it's kind of complicated. So let's run m out with array. Choose the weight. and then the covariance and variance matrix, and then you close transpose weight, and then multiply it with 252 to analyze it. So I suggest that you guys should press the Ctrl Shift Enter key because sometimes the Enter key is not working in for these formulas. Okay. So what are we going to do is that we are going to run 20k trials, which stand for 20k scenarios in the portfolio when the weights are randomly generated. And in the cells for standard deviation and expected return, I'm just going to set it equal to the standard deviation and expected return of the portfolio that I have calculated respectively. So we set this as anchor value, okay? And now we highlight the whole range to the bottom, Control Shift down, and then we go to data, what if analysis, and I'm going to use a little trick. I'm going to select in the column input cell and then run the trials by clicking any random cells and click OK. And now we have run 20k trials. As you can see that this is the efficient frontier of my portfolio. I have already generated, so I will going to reinsert it so you guys can easy to follow. Okay, so highlight the data, Control Shift down, and then go to insert a scatter chart. Okay, and now you can see that this one is kind of similar to that one, right? So the top left of the curve is where the optimal portfolio are located, because the top left part represents the highest possible expected return for a specific standard deviation. So the first thing we need to do is to fix the data point in the trials. We are going to copy all the data, Control Shift down, and paste it back to the top of the tables, and make sure to paste the value only, okay? And now you can see that the efficient frontier is now remaining stable here, right here, okay? So after we fix the efficient frontier, we're going to use the solver function to find optimal portfolio, but first we need to find out the risk-free rate. You could just take the current 10-year Vietnam Treasury bill, which is 3.161%, and the formula for the Sharpe ratio is going to be expected return subtracted by risk-free rate and then divided by the standard deviation. Now we're going to use the solver function to find the optimal portfolio with the highest Sharpe ratio. For the objective, we're going to set the Sharpe ratio to be the highest by changing the weight variable, and the constraint is the total weight has to sum up to 1. Okay, now we solve it. After we use the solver function, this yellow dot is the optimal portfolio with 29% of expected returns and 25% of standard deviation. So in order to optimize my portfolio, I should invest 75% in FPT, 18% in BMP, and 6% in EVF. As you guys can see on the efficient frontier, I have already inserted the dot. So I will try to reinsert the optimal portfolio so you guys can easily to follow, okay? So you guys go to design, select data. Well, I've already put it in here, so I will try to edit it. You click optimal portfolio, okay, edit. So for the series name, I put it optimal portfolio. And about the x values, it's going to be the standard deviation. And for the y, it's going to be the expected return. Okay, okay. But the special thing is here is that the optimal portfolio is not really laying down the efficient frontier, and it looks like it separates from the frontier, right? But I think this is just because we aren't running enough trials for the assets. To prove that my optimal portfolio is allocated on the efficient frontier, I want to review some fundamental knowledge. So the dots that you see on the screen right now are all of the portfolios with different weight assignments, and all of these portfolios are surrounded by a curve, which is the minimum variance frontier. And the efficient frontier is just the top portion of this curve above the global minimum variance portfolio. So in this part, we're going to draw a minimum variance frontier. So the minimum variance frontier is a parabolic curve, and every portfolio lying on this curve will have the lowest standard deviation for a given expected return. What are we going to do right now is to find the expected return range from the highest to the lowest one, and I'll show you guys how to do it. At first, I want you guys to copy this file and then move to it. But I'm not going to redo it because I've already copied it in here and rename it minimum variance. So in this worksheet, I'll show you guys how to find the expected return range based on the cells. Okay. So first, I want you guys to repaste the formula of these two to this one, okay, and also with this. So the reason why I want you guys to repaste these two formulas is because we're going to use these two cells to calculate the maximum return by using the solver function. And every time we use the solver function, these weight are going to change, and it will affect on these two variable. And as you can see that my optimal portfolio is based on these two cells. So I want you to fix these two value and so that the optimal portfolio will not change. Okay. So copy this and then repaste the value. Now we're going to find the maximum return by the solver function. First, solve function. Okay, we will change this cell with by changing these variable, and the constraint is going to be these weight is going to sum up to 1. Okay. Now max solve. So this is the maximum return. Okay. Now you paste it over here. Let's paste the value only. Okay. Value. Now we do the same with the minimum return. Minimum. Okay. Solve. As you can see that these will changing every time we use the solver function. So if we are not fix these two value, every time we solve by the solver function, this will be going to change, and also the optimal portfolio. Now paste this value over here. Okay. Now we can understand that the expected return range is going to be 31% to -9%. Now to find the minimum standard deviation for each return right here, I'm going to use the solver function to find it. Okay. Now we're going to use the solver. The objective that we want to set our standard deviation to be the minimum to min by changing the weight. And then we add some constraint right here, which is I want these weights to sum up to 1. And our expected return is going to be 31%. Okay. Now we solve it. So for the highest expected return, the minimum standard deviation is going to be 28%. Now we paste the value over here, and we do the same with the other expected return. And I will redo it with 25% of expected return. Okay. Objective to be minimum, and change this constraint. Yeah. The cell is going to be equal to 25%. So with 25% of expected return, the minimum standard deviation is going to be 23%. And then you paste the value over here. Okay. So I've already calculated of the minimum standard deviation for the expected return. Now we're going to use this data to create a minimum variance frontier by go to insert, choose a scatter, and I want to re-edit the, the data in this graph. Okay, edit this. As you can see that our x value is the standard deviation, but in this case, in this table, they took our expected return as x value. Now we're going to change it, okay? X value is the standard deviation, and also with this one, going to be the expected return. Okay, so this is how the minimum variance frontier looks like. Well, but haven't figured out how to combine these two graphs yet, so I've spent 20 minutes finding all of the minimum standard deviation for each expected return. And with this data, we can insert a minimum variance into this graph over here. Okay, by highlight all of these. Oh wait. Going to this graph, chart design, select data. We add a new legend entries, which called minimum variance frontier, and the x value is going to be the standard deviation, and the y value is going to be the expected return. Press OK. Now you press OK. Go up top to the top. So there is how the minimum variance frontier looks like. Well, I don't highly recommend you guys to collect all of the data by using solver function to calculate the minimum standard deviation for all of the expected return, because it will take you guys a lot of times. I just want you guys to understand what the minimum variance frontier is and how to draw it. Okay. In this part, we're going to draw a CAL, which is the capital allocation line. This line is a graph that visually represents the risk and return trade-off for a portfolio that combines a risk-free asset and a risky asset. So in this case, I will draw a CAL that combines the risk-free asset with my optimal portfolio. But first, we need to insert the risk-free asset to the graph over here. Now, to insert the risk-free asset, we're going to select the data. In this, I've already insert the risk-free asset over here, but I will try to do it again by going to edit. The x value is the standard deviation, the horizontal one, so it's going to be equal to 0. And the y value, which is the expected return, is going to be the risk-free rate, which is 3.16%. Okay, so this point is the risk-free asset, but I want to create some layout so you guys can easy to follow. Okay, so here, after we insert the risk-free asset, I want to assign some weights for my optimal portfolio right here. Okay, so capital allocation line, we put some weight in here, weight, return, and standard deviation. Now, I want you guys to think of the capital allocation line as an investment. So if we invest 0% in the optimal portfolio, we're going to invest 100% in the risk-free rate. So return is going to be the first weight multiplied by the expected return plus 100% of risk-free asset multiplied by the expected return of risk-free asset. So return is going to be 3.16%. Now, if we invest 100% in the optimal portfolio, the return is going to be 100% multiplied with the expected return and 0% in the risk-free asset. Multiply. Okay, so this the return of the risk of the optimal portfolio if we invest 100% in it. Now for the standard deviation is just equal to uh, the weight of the optimal portfolio multiplied with the standard deviation, because right now the weight of I mean the risk of the risk-free rate is equal to 0, so we don't need to calculate it. Also with this one, with standard deviation. Okay, so now we're going to plot these data into the graph. I go to select data. Now for the capital allocation line, the x value is always going to be the standard deviation, and the y value is going to be the expected return. And you can see right here, this this one is optimal portfolio, and this one is the risk-free asset. Now I want to graph it up by go to change chart type, line, scatter, this one. Okay. So this is the capital allocation line that you see on the screen right now. Okay, so I have just been crashed out, so I'm going to draw the capital allocation line again. So I'm going to draw the capital allocation line on this chart because I don't know why, but every time I change the chart type of this graph, I have a crash out. Okay, so for the weight, I'm going to invest 0% in optimal portfolio. The return is going to be uh, the weight of optimal portfolio multiplied by the expected return. I want you to log it because the next time we change the weight, we just need to drag it down so we have the result easily. We don't need to type it again. Okay, so minus 0% multiplied by risk-free. So this is the return of the CL if we invest 100% in the risk-free asset, which is 0% in the optimal portfolio. Now with 100% with the optimal portfolio, we just need to log it first and drag down. So this is the return if we want to invest 100% in the optimal portfolio, and this is also our optimal portfolio. When we round it up, it's 29%, and for standard deviation, it's going to be this weight multiplied by the standard deviation. Log this, and then round it up. So you can see right now, if we invest 100% in the optimal portfolio, this is the same as this one. So we're going to draw the capital allocation line by add some data into this graph. First, we need to add the risk-free rate first. Risk-free asset. X value is going to be equal to 0, and the Y value is equal to the risk-free rate. Okay. So, this is the optimal. This is the risk-free asset. I will add some data here. Now I'm going to add this data into this graph so we can see the capital allocation line. Go to select data again. Now we add CAL. X value is the standard deviation, and the Y value is going to be the expected return, as always. Okay. So this is our capital allocation line. It's not very accurate because I need to reinsert it into new in the new graph, but I want to extend it further. Okay. Now we assume that we're going to invest 200% in the optimal portfolio with leverage, of course, and now the return is going to be 25%, and the standard deviation is 0.9%. Now the capital allocation line will look like this. Select data. We edit this one. Edit. I want to take off these standard deviation and of these return. So now this looks more accurate. So this is exactly how to draw a capital allocation line. And in this video, we have go through how to find the optimal portfolio, how to draw efficient frontier, how to draw a minimum variance frontier. So that's the end of our video. And I hope that you guys find this video helpful. Hope to see you guys on the next video.